Good afternoon. Thank you very much for coming along to this session. Just when we thought it was safe to come back here, I'm back. And I'm going to be talking about the neuroscience of pain, which may seem like a really odd subject, a terrible, horrible subject to be talking about. But I am going to try to make this as painless as possible, looking at the positive effects of this. Can there be anything positive about this? Well, I'm sure we're going to try to have a look at this with you. We're going to be exploring some things which might be a little bit deep for what you might be interested in. But the number one reason for people visiting their physician is pain. You can get along with most things. You can be living around and think, oh, I can manage to get from A to B living along. But if it's causing pain, that's the main reason for going to see a doctor. You might have a cracked tooth, and you might think, oh, I can sort of live with this. But if it's hurting, then you go on to the dentist. So pain is a great motivator for us, and it'll be really interesting to see what pain actually is. And hopefully, when if you suffer from anything painful, this might give you some confidence to talk about your condition to a physician, because you won't just be palmed off with a few doctors. You can actually answer some questions. So looking at the neuroscience of pain, and this is such an important topic because it is a warning light. Just as we have on our cars, on all sorts of devices, whether it's working properly or not, and then we have all these things. It causes us a bit of a shock when we're driving along and the engine light comes on, or whatever. And you could be having a nice conversation, planning out the day and thinking, oh my goodness, the tire pressure's low, or whatever. So it turns your attention from one thing to something that is really important. So that's why pain is such an important sensation. So I thought I'd try to get you interested in all the positive aspects of this. And there's a school of thought that you can't really experience pleasure without pain. That people who are insensitive as far as the sensation is concerned, it's difficult for them to really experience what pleasure is. That you only know one with the other. So I hope I've sold you on that first one. It's also a tool for growth and resilience, in that if someone were to tell you a story about how they battled through a really painful thing, you think, gosh, that's pretty good. They managed that. It's a painful situation, but they managed to get through that, and they're quite resilient to come out the other side. Whereas if it's just told a story where, I just went and everything worked out, it's less interesting. It is a social connector, in that people, the older they get, they start sharing all their pains and their woes, and so I have a pain money, I've got a pain money as well, and then off it goes, like that. So, that's important as well, because it shows that we're not alone in all of this, but there is a connection with other people. It's very much an evolutionary device, and throughout our development, as we encountered more painful things as we went along, it did help us to avoid whatever. I remember when I was a child wondering what electricity was. I still wonder what electricity is, but at that stage I was thinking, my parents were talking about electric things. You plug things in, just straight in, you plug it into a wall, and something, television lights up or whatever happens. And I thought, I wonder what there is in there. And so I took one of my mother's knitting needles, and and I thought, let's see if I can get some electricity out. And I did. And I remember like being at the other side of the room. The most important thing was I didn't want my parents to find out what I had done. So that was the number one thing. It didn't matter that my arm was all anaesthetised, or I had to put the knitting needle back and hide that. On another occasion there was a fire going, open fire, and it just looked so beautiful with all the colours, the red and the orange and the yellow, and it's a nice feeling. And my parents said, do not go near the fire, don't touch it or anything. And I thought, oh, this doesn't look good, and I'm going to put my hand to the fire, and that's the last time I ever investigated a fire. So, these are things that we tell kids, we have to experience some of them ourselves. But, like through evolution, we find if you fall, you can't hurt yourself. So let's try our best not to fall. I want to do things. I'm not a psychiatrist or a psychologist. Ideally in the brain rather than the mind. But the two are intimately connected. So, I sometimes go into the more mind areas. And if you do have if you're positive about your condition, it does help enormously. I don't know exactly how, but if you were to tell a patient, take these tablets because they're really good, they're likely to help you, they will help them. It's amazing. You get the same tablets, it doesn't say anything, well, we'll give these a go, and see, you can always change that. It won't be as effective. So there is a psychological aspect to all of this. So positive emotions definitely help with pain management. And linked with that is all the mindfulness, the psychological aspects. I know we saw childbirth and all this. There's a whole load of advice around that. People want to avoid any drugs or medical intervention. There's a whole load of things around that. So if you have changed your mind about, this is a horrible subject to talk about. This is a really interesting subject. And there's lots of work being done in this. So let's start with what pain is. Pain is defined as an unpleasant sensory and emotional experience associated with actual or potential tissue damage. Pain is one of our senses. When you ask lots of people about how many senses we have, not many of them say about 5. The usual smell, taste, vision, etc. There are hundreds. We have hundreds of sensations. And those are the 5 ones that most people know. Pain is a sensation on its own. It has its own pain receptors. It has its own, the brain has ways of perceiving pain. The nervous system has ways of conducting pain, altering it. So, it's very much a sensation on its own and needs that attention. So to understand what underlies pain helps with its management, helps with treatments. And there are 3 main types of pain. There's something called nociceptive pain, which is, we'll cover that. If you're not sure what that means, we will cover that. There's inflammatory pain, inflammation, pathological pain. We'll be teasing what that means as we go along. The odd thing is that the sensation of pain only occurs inside our heads. It occurs nowhere else. So whenever you feel a pain in your toe, in your knee, elbow, or whatever, it's not occurring there. The origin of the sensation is obviously there, but the actual sensation does not occur there. It occurs in the brain, which is why it's my domain. And strangely, the brain itself does not feel pain. It generates the perception of pain, but it feels no pain. And we know that the brain doesn't feel any pain itself because there are no pain receptors in the brain. You can open up someone, conscious, press all over the brain, structural substance itself. It evokes a whole load of different sensations. None of them are pain. So, it seems like a contradiction. The thing that generates the sensation itself feels no pain. So let's look at the different types of pain. I'm painting all this with a broad brush because there isn't time to go into all the detail. But this nociceptive pain is the pain you usually feel if the skin is broken, if there's an injury, anything like that, where it's either damaging tissue or there's a potentially going to damage tissue. So if you just stick a pin, anything that breaks through the skin, anything that might be inside a splinter, all of those things are all part of nociceptive pain. And we call it that because it activates receptors, pain receptors, which are called nociceptors in the trade. Or we could just call them pain receptors. They're the same thing. So when you break through the skin, for instance with a needle in this diagram, people associate that with pressure. Pressure has its own receptors, so pressure is not pain. But then it gets to a certain stage where it starts to damage tissue and it activates these receptors. It generates signals that I'm going to cover in the next slide where that goes. So that's one type of pain. Another type of pain is the neuropathic. So these are neuropathies, and they're caused by dysfunction in the neurons. Various things happen in the neurons, and they generate signals which then are taken to the brain and interpreted as pain. And things like inflammation as well. There's loads and loads of inflammatory disorders. I'm sure we've all suffered from one of those at some time, and they're extremely painful. And hopefully at the end of this session, there should be enough time for questions. So please keep any questions in your mind. So what happens with nociceptive pain, the pathway? So in this diagram here shows a pin affecting skin on one of the fingers. It's gone deep enough into the tissue to cause tissue damage and to activate these nociceptors, these pain receptors. And the pain receptors send information down the arm, along the arm, all the way to the spinal cord. So that's the diagram of the spinal cord at the bottom. And all of that is one single fibre. There's no connections along the way. So it goes all the way from there, along your arm, and then to your spinal cord. In this case, in the neck, or if it's somewhere in the leg, a bit lower down in the spinal cord. And have a look at that pathway, because what happens is that it crosses over to the other side of the spinal cord. So if you remember, one half of the hemispheres looks after the opposite half of the body. And so this is how information goes at the spinal cord. Instead of like going into the spinal cord, going up, it crosses over, it forms a synaptic connection with an ascending fibre that goes to the brain, goes to this thalamus, then goes to the cerebral cortex. And if you remember, there was a homunculus that is drawn on the side of our cerebral cortex, and that has a huge part of it is dedicated to that, to actually feel it quite badly when there's a finger or part of the hand. And it goes to that part of the cerebral cortex and it activates it. And what it does is that it sends down fibres, the descending fibres, goes down the spinal cord, and then it goes to muscles that help with the reflex. So you touch something sharp and painful, and you don't just leave it there and think, oh, that's painful. You have a reaction, and you have the withdrawal reaction. Now that's what happens in the normal reflex. It's a little more complicated than that. So, when I explain it to students, and I say, if you were to touch something hot, your response is withdrawal when you drop it. But not if it's your dinner. Not if you've been slaving over something, and you don't want to play, and it's really hot. You don't withdraw. You hold on to it. You're okay with the table is waiting. You rush over, and you put it down on the table, and you sort of like roll your hand on sort of run it under a tap. So we have a mechanism that can override all our reflexes, and we put a value on what that hot object is, and we say, is that something we can let go and let it smash to the floor, or is it something we can perhaps risk a little bit of tissue damage and take it over to the table, and we make that calculation quite quickly. We of course are not determined totally by reflexes, because otherwise we wouldn't be able to have an injection. That when you go for vaccination or something, they stick a needle in, you don't flinch. Well, you might flinch a bit, but you don't go running around. They have to catch you or things like that. You grin and bear it, and you think it's going to hurt, but this is for my benefit, and it doesn't matter if it hurts. I'm not going to put up with this. So those are your reflexes. If someone just came up behind you and started you would react like that, because it's obviously unprepared. Same for dental work. So anything where it might be uncomfortable, just hang on in there. And what we do is we send fibers down, inhibitory fibers, that say try not to flinch, try not to move, things like that. So. And just as an aside, I've had some problems with my knee. And I remember going to see a consultant, orthopedic consultant, one of the hospitals in Bristol. And he said, well, we're going to, what we can do is give a steroid injection into your knee. And so I thought, well, I don't particularly want to have this, but if it helps me. And I said, okay, go for it. And he produced a really long needle, thick needle, with a syringe, and he sort of filled with that. And I was thinking, where is the nurse that's going to hold me down? Yeah. And so I said, is anyone else doing it? No, you hold your knee. Hold your knee still. And, and I was thinking, pay someone, get someone just hold me down. I thought, no, this will behave like that. And so I just held my knee still myself, as he was approaching with the needle. I'm not really scared of needles most of the time. Not when it's a great big thing, and it's not just a jab, but it has to be manoeuvred into the right position for something or part of the knee. And because I can visualise all of that going on anyway, it just makes it worse. So I'm thinking, the tip of the needle is just there. And he eventually sort of got to the right place, and then he started to empty the syringe, and that hurts itself. And I hadn't realised that when you're really fearful, the autonomic nervous system fires, and I was covered in sweat. Sweat you've never seen before, no experience. It was absolutely wet all over, because it was such an attack on the system. And I had to hold the knee steady. So, and he probably thought, because I knew a little bit about all this, I could control my nervous system. I can't. I'm human, just like, stick a needle in me and I feel everything. So there are ways of overriding this. one of the main problems with treating someone with pain is because pain is so subjective and everyone has their own way of describing it, it's really difficult to take a history of it. So the subjectivity of pain is such that you can feel pain without anything being done to you. So, when the dentist approaches me with a drip, I'm feeling it, and nothing has been activated at all, apart from my imagination. I'd be terrible if I had to undergo torture. I'd be giving names of everyone before anything is done, because So it is highly subjective. So you can imagine what it's going to feel like before anything is done. You haven't had your nails pulled out before, or you haven't been on a rack or anything like that. You can imagine what will happen. Another problem is that when you take the history, there's things like location. You think, it's quite easy taking history of someone with problems of pain. There's no evidence of the pain, unless it is nociceptive pain. There is no evidence. Someone comes in and has had pain on the side. You can't see anything. Even if you did a scan, you couldn't see anything. And this business of certain sorts of pain there's no evidence of, I learned when I was a school kid, because I found you could have a stomachache and get off school, and there's no evidence of it. You just have to pull these faces and bend over and complain. But it's worse when a patient can see you and you're trying to assess them, because they say, I have a funny pain. By funny, what do you mean? And they sort of explain it in their particular way. Where is it? Where are you feeling this? And you've got to tease out things like, how intense is the pain, on a scale of, 1 to 10, how severe is it? What scale is that? We don't have a scale 1 to 10 of the pain or thing. Pain at 10 is like, I don't know, have an almond off or something. And we've all got a different 10 on the scale. Added to that, location of pain. Now, you probably have heard of referred pain, and this is where you sort of say, I've got a pain in a particular place. The pain doesn't always originate there. That's where it is referred to on the skin. So this business of, if you have angina, you have this feeling down your arm and on your shoulder. If someone said, they've got a heart problem, say, why do you think that? I say, well, it's in my heart, I can feel it in your heart. That's the last place it would be. You don't actually feel the pain in your heart. It's referred to your shoulder and to your arm. And the reason why it's referred there is that's where the heart tissue originated from during the fetal development. And it's similar for everything else. When you'll divide your abdomen into quadrants, and each of those quadrants reflects certain organs in your digestive tract. So you say to people, find this drop across on your tummy, where would it be? And you can sort of guess, but it's not easy. And this is a map showing, it's roughly where things are. So most of the things that go on inside us are referred to our surface, but that's not where the pain originates. So that's an added complication. I'm going to go on to the sort of, but anyway, we're going to go on to, what can we actually do? I don't want to just wallow in pain, but have a look and see what things we can do to help people. So this is all about analgesics. This is how pain is treated, one way pain is treated. And one of the earliest ways that pain was treated was through opium. and obviously don't use that now, we use derivatives of that. But that was one of the earliest ways. And it's been described in ancient writings for way back when, from the Sumerians, 4,000 years ago, 4,000 years BC. So it's a long time ago. And that spread from there to other countries by Arab traders that were going around. There's also, as you know, there's the willow bark, the willow tree, and if you were to take the bark from it and chew on it, it gives some relief, and that's where aspirin first was found. But at the time of Hippocrates, or he was suggesting about chewing willow. In the Middle Ages, in Europe, other plants were used, things like mandrake and henbane, laudanum. Nowadays, we use those sorts of chemicals, but they are all synthetic derivatives. All of them cause various side effects, trying to get rid of the side effects. A lot of them are these synthetic drugs. We'll come on to some of them. So as well as managing pain is concerned, there's two types of pain. There's acute pain, chronic pain, and the drugs of choice that people start with before ramping up things are called non-steroidal anti-inflammatory drugs. I don't know whether if you've come across those before. So you can have steroids, you can have non-steroidal anti-inflammatory drugs, and these include all the favourite ones that most of us have used at some point: aspirin, ibuprofen, naproxen, and all of those drugs, the non-steroidals, all of them reduce a chemical called COX-2, which is cyclic oxygenase. It's an enzyme, and that is a mediator of pain that's produced by a class of chemicals called prostaglandins. Have you heard of prostaglandins at all? Yeah, some of you have. And I remember when I started off as a student, there was a book, and it was called Prostaglandins. Never came across this one before. And I just opened it up, and it said, prostaglandins are the most ubiquitous substances in the body. And prostaglandins are a major group of chemicals. They mediate everything about us, and people haven't really heard about them before. So I think this was in about the 70s or so, this book was written. Before then, no one knew about prostaglandins. It was almost an overnight sensation. Were prostaglandins found before that? Yes, they were. But people thought they were byproducts of other reactions. So it was a mindset. They found these, and then they thought, well, I don't know what they are, so it must not be important. And then someone stuck their head above the parapet and said, because it's only around, perhaps they might be doing something. And he said, no, that's ridiculous. And that person was absolutely right. And so it was a mindset of people, well, let's look at this in another way. And you know what? Whatever processes occur in the body, prostaglandins are involved. In virtually everything. I can't think of anything they're not. So cutting that down to mediating pain, they're very much involved in that. And so what non-steroidals do is that they block the action of a chemical that mediates prostaglandin action. So that's how aspirin all works. Aspirin was found before prostaglandins. So people happily took aspirin without knowing how it works. And that legacy still applies today. Like, if you might come across people who say, you know what, we take aspirin, no one knows how it works. There was definitely a time no one knows, and now we know definitely how it works. So it works through this pathway. Opioids have been around long before we understood anything about how nerves work. So in this diagram, it might look a little bit complicated, but there's a nerve terminal. This is the end of a nerve. A potential electrical signal would come down to the very end, and then at the end, the electrical signal then causes a chemical reaction to occur inside the nerve terminal, and it releases neurotransmitter. The neurotransmitter then diffuses across to the other side, across the gap, the synapse, and it activates the other side by combining, holding on to receptors on the other side, and it causes an electrical reaction to come off the electrical thing goes. Now, when I knew less than I know now about all this, when I started studying it, I was thinking of a ridiculous way for these things to work, because it would be better if you just have the electrical going into electrical. Why have this sort of structure there? Because this holds it up. There's a synaptic delay. And obviously, it's therefore a very good reason that I now appreciate fully. This is a valve. So you can only get information going in one direction. It gets down the nerve, it becomes chemical, it becomes electrical, and then comes on. It doesn't go the other way. So if you were to excite the muscle or the other cell, it doesn't activate the thing, the nerve innervating it. So it's a very clever system. It directs the information. And this is the basis of our memory and how we work. So how do opioids work? Well, if you can see on the nerve terminal, you've got nothing there, the structure that spans across the membrane. And what happens there is that the opioids attach to that on that terminal, and it stops it releasing the chemical. And that's how it acts. So this is it's a modulator of what goes on. So it's not just the chemicals released, but it's modulated by this. Now, opioids are never found inside the body. So this thing from the poppy seed and all the chemical, nothing like it is found inside our body. Yet there are receptors to it on nerve terminals in the brain. So that's quite remarkable. Why should that happen? And it shouldn't. And what it is that we have an equivalent to opioids inside us. They don't work in the same, they're not identical to opioids, but they're called endorphins. And I'm sure you've all heard of endorphins.
Yeah.
And endorphins come in when you are extremely stressed, in stressful situations. And what it does is that it's released by the nervous system, and it acts like the opioids. And what it does is that it calms down the nervous system a bit. So, and people talk about an endorphin rush and things like that. So, I'm sure all of you have had a local anaesthetic at some point at a dentist.
Yeah.
Yes. It's applied as a gel, as cream, injected. So there's all sorts of different ways of applying it. And I thought I'd just cover, if you're interested, how local anaesthetics work, because it is quite fascinating. On a top diagram, that's our friend, the neuron, and an electrical signal goes from the cell body to the terminals, as we know, and we also know that it now jumps. So those little gaps you have, given a grant having no neurology, why you found them, it jumps from one of those spaces to the other. And it jumps from one space to the other because it's like queue jumping. If you were to queue up for something, it would take you a while. If you queue jump, you get to the front faster. And so this jumps. It's given a term called saltatory nerve conduction from the Latin meaning to dance, saltare, to dance. So it's like dancing, it's jumping along. And that's how we achieve speeds of 50 meters per second along some of these nerve fibers. What is there at the nodes? What is there at the app that allows the signals to form? And the answer is these things, the sodium channels. And sodium is the mediator of the electrical signal. Sodium is outside the membrane. It passes through the membrane, not willy-nilly, but passes through channels. And these are proteins that are inserted all the way in those nodes. And it's closed. And then a signal comes along, it opens, and sodium goes in. So in our first diagram, you have sodium not going in because out imposed. A signal comes along, it opens, sodium goes through. And then sodium is going to bottle it off. So it's the sodium going through these channels that is actually the electrical signals. If something were to block sodium going through, the signal wouldn't continue. That something is a local anesthetic. So the local anesthetic is a chemical, a molecule. It attaches to the channel and it stops the sodium going through. And so when you go to the dentist or wherever, they give you a local anesthetic, it is that. It's blocking your channels, stopping the sodium going through. It's important for local anesthetic that eventually comes off. So it is broken down. It lasts for a certain amount of time, and then it comes off the channel. The first local anesthetic ever found was cocaine. I sort of mentioned cocaine before in relation to Freud. So it's a chemical stimulant, cocaine, from the coca leaves of various places, Peru, Colombia, in South America. And the native Peruvians chew them for this stimulant effect because they're at high altitude, they do lots of work, strenuous work, and they've got into this thing of they chew the coca leaves. But there's only about 0.5% to 1% of active cocaine in a leaf. So it's a relatively low level. So they don't get all the effects of cocaine addiction, although they are addicted to it. So even when they're not doing strenuous work, lots of it's still chewing, because it will be habit forming and addiction. And it does give them a euphoric effect. The first Western report of cocaine, natural cocaine, was in the 15th century by Vespucci, who reported it. So historically, it's been used for medicinal and for local anesthetic use, but it is highly addictive and dangerous. I think I might have mentioned that there's huge blood supply to the brain. No blood actually makes contact with the brain. It goes to the brain, but no blood actually makes contact. If it did, there'd be a serious problem. Instead, there's a barrier, and it's called the blood-brain barrier. And what happens is that substances that are in the blood don't automatically go into the brain. It needs to pass through this barrier, and the barrier is selective. So it allows things like nutrients and oxygen and glucose to pass through, but it stops quite a lot of things. And the reason is that it's protective of the brain. So when you eat a cake, and if I were to monitor the amount of glucose in your blood, there would be a spike. And it would be a spike, it wouldn't remain high, it would be brought down by insulin If you were eating crisps or anything salty, there'd be a spike in your blood. And then it would be brought down by various hormones and things. So it'd be regulated. The brain could not tolerate spikes. It needs to be in a stable environment. So this blood-brain barrier, then, because if I was monitoring these things in your brain, they wouldn't be spiking at all. It would all be at the same level. So we have another circulatory system. So we have cerebrospinal fluid, which is the substance that actually is in contact with the brain and the spinal cord. What I'm trying to say is that it does act as a filter, but cocaine goes through. And a number of chemicals, a number of drugs goes through. Alcohol goes through. The blood-brain barrier, unopposed. Cocaine goes through. So not only do you have the anesthetic effects on the periphery, but it also goes through into the brain. And because of that, action on the brain, as I have passes through the blood-brain barrier, to increase dopamine levels, what we come across dopamine. It's the neurotransmitter for reward and pleasure. And so when dopamine levels are high, you feel good about yourself, feel good inside. And so this artificially brings up the dopamine levels. And so you get euphoria, you get alertness, which lasts for a certain amount of time, followed by a crash as the levels go down. And you feel fatigued, depressed, there's intense cravings, paranoia, cardiovascular effects, hallucinations, a whole load. It's payback time. And because of the euphoria and the way that addiction occurs, you want to take it again, despite all these horrible things from going on. So we have local anesthetics, of course. Cocaine is no longer given, but lidocaine, there's a whole certain range of synthetic local anesthetics that are being produced that don't pass through the blood-brain barrier, don't have the same stimulatory effects. Just looking at the time, so there's a whole load of different types of analgesics here in different situations. I've just picked out a few, so it's not in any particular order. There's epidurals, which I'm sure you've all heard of or come across. So as you can see in the diagram, the cross-section of the spine, that you have the spinal cord. People often call the bony bit the spine. The bony bit is actually officially the vertebral column. So that is the vertebral column. The spinal cord is reserved for the nervous bit. So the spinal cord is the bit in the middle of that diagram, is protected by the vertebral column, the bones of vertebrae on either side. And it is quite a dangerous procedure. I mean, anything that's invasive is dangerous. But you can see that this goes into the space, the tube, the needle, goes in between the vertebrae. It goes through the membranes that protect the central nervous system, the three membranes, and it goes into the space, and an analgesic is put in there, which then removes a lot of the sensation then from that level down. Now, can you see that the spinal cord, injecting into the spinal cord, anywhere near the spinal cord, is a no-no. The minute you put a needle in, you could damage the A70 and D70 fibers in there. But they tend to go fairly low, and the spinal cord at a particular level is not just one solid piece of tissue. It divides up into finer bits. It's called the cauda equini, and it literally means horse's tail. And so it becomes like a horse's tail from a certain point. And so because it's smaller fibers, when you inject, they can move more so than with the tissue. A whole load of complications you can get from that. There's trigeminal neuralgia, someone mentioned it. Has anyone suffered from this? extremely painful, and it's one of the cranial nerves, and the trigeminal nerve has 3 branches. One goes around the eye, the other sort of like the cheek, and another around the jaw. And if you get any damage to that, so you could get inflammation, you could get a little tube or something that presses on the nerve, it causes the most awful pain. Almost, but it's just an awful pain, and it's so difficult to manage. There are drugs and medicines that you can give. In some really severe cases, has to be cut because it's just so painful. But what you can see in the diagram on the right hand side, the sort of area that's affected, and especially if it's over the eye and things. So I promise not to be gory, but sorry about that. I'm going to finish off with this and then see if there's any questions. You've all heard of botulinum toxin at some point. When I started my career, this was the first toxin I ever experimented with. It is the most toxic substance known. There's nothing more toxic than this, especially on the nervous system. And I had a vial of it, glass vial of the pure toxin, and I was working in London. And had I diluted that and injected that, that was enough to kill the whole population of London. It was about 9 million at the time. So it's highly toxic, just a tiny amount. And this toxin is produced by an organism, Clostridium botulinum, and it causes paralysis. It doesn't pass through the blood-brain barrier. It only affects everything outside of your brain, which means that when you're paralyzed, you are aware of it. So you might be lying down, to everyone else you look unconscious, but in fact you're aware of everything that's going on. You eventually will die if not treated. Well, there is no treatment really. You will eventually die because it affects your respiration. So you're not able to use your respiratory muscles. And it started off, it was really recognised. People knew about it beforehand, but it was really came to prominence because there was a party going on in a German village in the 1800s. And it was at a time when the canning process was not perfected. And these villages bought a whole load of tin sausages. And these tin sausages, the sausages in them, they were sterilised, some Clostridium botulinum were inside. It reproduced, it infected the sausages. This whole village came together, this town came together to celebrate. And they opened the sausages, they had their own buffet table, they were drinking lots of beer and everything, had a fantastic time. They ingested it, and nothing happened for 24 hours. This toxin takes 24 hours to act. When the big hand got to 24 hours, they all fell down. And they were totally paralysed. And in fact, the majority of them died. And when sort of like, maybe all the village came to have a look, they found more like this, they didn't know what it was. Eventually it was found to be botulism. And the word botulism comes from the Latin for sausage. So that's the origin of that. It paralyses muscles, and there is no recovery from the paralysis. It goes to these nerve terminals, no recovery. When we're talking about botulinum, as Botox is given to people, what on earth am I talking about? The most toxic substance, then you fall down, paralysed, and yes, it's injected into people who are not doctors, they're people who work in the cosmetics industry. So when people say that to me, it is China, except that there are 8 types of it. Type A is the most toxic. That's what I work with. And the one that's injected into people for cosmetic reasons is one of the lower ones, right down the bottom. So it is less toxic. It does have clinical uses. It does paralyze muscle. In some cases where pain is due to the muscle, it can relieve pressure quite a lot. But myself and colleagues developed a technique to treat a disorder called torticollis. I don't know whether you've heard of it. Torticollis literally means tortured neck. And people don't realise just how important the neck muscles are. Because we use it to obviously move one part of the body, the head around, and we do that with enormous precision. So we can sort of move it by only a degree or so in any direction, enormous in a direction. So the control of the head movement by the neck muscles is really important. There is a disorder called torticollis where someone, it's just like us, they wake up in the morning and their head is pulled in one direction. So it's like that, and then they can't bring it back to midline, and so it's pulled like that, and it can be in any direction at all. And there was one patient we saw whose head was like that, and when she was watching TV, she had to sit 90 degrees to the TV, and had to do everything 90 degrees. And the old-fashioned way of trying to treat that is to cut some of the nerves that supply. So it's caused by overactivity of nerves. So if this side is overactive compared to that side, then the head is pulled over that side. And if you try to cut some of the nerves to the muscles there, the head sort of goes more back towards the midline. And we found a way that we could give a chance to paralyse the cutting nerves. And it worked relatively well. The head was sort of pulled more or less back. It's very difficult to get right. So hopefully that's introduced you to pain. It wasn't too much for pain, and you got something from it. It was all produced at short notice, so I hope we managed to hit a spot with everyone. And I'm here for questions, so if you don't want to ask a question now, just come and see me.
I'm going to ask about Bell's palsy.
Bell's palsy?
Bell's palsy, yeah. Somebody in our family got that just one day. It looked like they'd had a stroke.
Yeah.
So and it dropped one side of their face.
Yes, that's due to a cranial nerve.
Yeah.
That affects the face.
Yeah.
And for some reason it stops. There's a number of reasons. One is you could get inflammation that just develops. It presses, anything that presses on the nerve will stop it acting. And so what happens is that if it is inflammation, they're often given anti-inflammatories to start off, and most people respond to that. If it doesn't, they look more carefully, and it might be damage to the nerve.
It did eventually go after about 3 months. It went gradually, and they said it was due to stress that brought on this. Is that something you've heard of?
Yeah, I mean, it is really difficult to comment, but yes, I mean, I can't quite see at this moment, but I'm sure it's a contributing factor. But it's usually something physical. It could be the stress could have affected the blood supply. So yeah.
Okay, thank you.
So if you want to ask a question privately, please do so. Otherwise, hopefully I will see you again.
Thank you. Thanks for that. Thank you.